In this video, we are going to start the preparation methods of ethers. Okay, so the first method that we'll be discussing is the preparation of ethers from alkyl halides. Okay, this particular method is known as the Williamsons synthesis. Okay, so the first of all, we can prepare the ethers from alkyl halides by Williamson's ether synthesis, and we can also prepare ethers from the alcohols by the dehydration of alcohols, as well as the means by the acid catalyzed dehydration, as well as the catalytic dehydration. Okay, and from alkenes we can also prepare ethers by the addition reactions. So in this video we'll be discussing only the first one, that is the preparation of ethers from the alkyl halides, and in the subsequent videos we'll be discussing the other methods as well. So in Williamson's ether synthesis, what we do, we take an alkyl halide and we react it with alkoxide. Okay, we react it with the alkoxide, particularly we use the sodium alkoxide, and the resulting product of the reaction is an ether. Okay, and sodium comes out with the halide ion as a salt. So this is a very important laboratory method by which we prepare the ethers. Okay, so we react alkyl halide with the sodium alkoxide, or we can also use sodium phenoxide in case of aryl ether. In case of the preparation of aryl ethers, we use the phenoxide ion, sodium phenoxide. Okay, as we have shown in this example, we're reacting alkyl halide with the phenoxide. This is phenoxide ion, sodium phenoxide ion. The reaction between the two gives us again the ether. Okay, so this is what is known as the Williamson's ether synthesis. It's a very important method of preparation of what you call as the ethers industrially. Okay, so we can prepare both alkyl ethers as well as aryl ethers by this method. So we have some important points regarding this reaction. First of all, the reaction proceeds. This involves the SN2 mechanism. The mechanism by which the Williamson's ether synthesis proceeds is the SN2 mechanism, which is the substitution, one of the substitution reactions. Okay, this is a substitution reaction. This is a substitution reaction, SN2 nucleophilic bimolecular substitution reaction. Okay, we will learn about these nucleophilic reactions in detail in some other lectures, but here we have to just remember that the reaction, that is a Williamson's ether synthesis, it proceeds via the SN2 mechanism. Sometimes we are asked this question, that by which mechanism the Williamson's ether synthesis proceeds. So we have to write SN2 mechanism. Okay, nucleophilic substitution bimolecular reaction takes place, and in that reaction we get the ether. Okay, so this is Williamson's ether synthesis, the mechanism which is followed by this particular synthesis method. So there is the attack of an alkoxide ion on the primary alkyl halides. Why only primary? Because primary alkyl halides are actually the ones that react by SN2 mechanism, that involve the efficient SN2 reaction. Okay, in secondary and tertiary alkyl halides, we can say there is no SN2 or very poor SN2 mechanism shown by secondary alkyl halides, and by the tertiary alkyl halides the SN2 mechanism is not shown at all. Okay, so the reaction is between the alkoxide ion and the primary alkyl halides. They react very efficiently. This method is a very good method for the preparation of unsymmetrical ethers, although we can also prepare symmetrical ethers by this method. And the nucleophilic substitution reaction that is involved in this particular method leads to the formation of the desired products. How? That will be seen in the examples. So this is the general mechanism of this reaction. Very simple mechanism, because it is the SN2 mechanism. So what actually the first step is the preparation of the alkoxide or the phenoxide ion. So it is by the reaction of the reaction of alcohol with sodium metal. When these two react, we get the alkoxide ion. Okay, so this is the first step of the reaction. The first step of the reaction is the preparation of this alkoxide ion, and that is prepared by the reaction of the alcohol with the sodium. Or in case of phenoxide, we react a phenol, as we have studied in the previous section. So in that case, we react phenols with the sodium, and we get the sodium phenoxide ion. In that case, we get the sodium phenoxide in that case. Okay, so this is general mechanism here. So this is the first step of this reaction. In the next step, there is the attack of the alkoxide ion, because it's having the negative charge. There is negative charge on the oxygen. Okay, and due to the electronegativity difference between the carbon and halide of the alkyl halide, there is a little polarity in the bond. Okay, so there will be a small negative charge on the halide ion, because it's more electronegativity negative than carbon, because this R represents an alkyl group or an aryl group, and definitely there is a carbon which is directly attached to the halide ion. Okay, so halide being more electronegative and negative, there is a small negative charge on this particular atom, and a small positive charge arises on the carbon atom. Okay, so there is an attack of this oxygen on the positively charged carbon atom, which leads to the subsequent removal of the halide ion, and this all takes place in a single step. Okay, there are no multiple steps involved. This takes place in the single step. That's why it's called as the concerted mechanism. Okay, the SN2 mechanism is the concerted mechanism. That's bond formation and bond breakage takes place in a single step. Consequently, the bond is broken and the new bond is made subsequently. Okay, and in this reaction we get the product ether. Okay, so this is the second step of the reaction. This is just a simple mechanism that we have to remember. We'll just take the particular examples also. So this is an alkyl alkoxide. This is an alkoxide. The alkoxide ion, and we have alkyl halide in this case, and this is the ethyl bromide. Okay, this is ethyl bromide. In this reaction, again, the oxygen being negatively charged, that attacks the carbon, which is having a positive charge, and actually this carbon is having the positive charge. The del positive charge will be on this carbon, not this. Okay, because this is directly attached to bromine. So the attack will be on this carbon, and we'll be getting the resulting ether will be this one. And this is the symmetrical ether, and this is the diethyl ether. Okay, similarly we can also form the unsymmetrical ethers, as we have an example here. Okay, we have an alkoxide that reacts with a methyl bromide, and we get what you call as the unsymmetrical one. This is the unsymmetrical ether. Okay, this is unsymmetrical ether, example of unsymmetrical ether. And one more example here we have of phenoxide ion. Phenoxide ion reacts with the methyl bromide, but we have two major limitations of Williamson's ether synthesis. First of all, because the reaction follows the SN2 mechanism, as we already discussed. It follows the SN2 mechanism, and if we know the SN2 mechanism is very efficiently shown by, or is applicable to, what you call as primary alkyl halides. Secondary and tertiary are very poor, rather we can say tertiary alkyl halides do not show the SN2 mechanism, and 2 degree is very poor to show the SN2 mechanism. So the formation of what you call as the reaction of 2 degree and 3 degree alkyl halides with the alkoxide, they do not undergo the SN2 mechanism. They rather undergo what you call as the elimination reaction. They show the elimination reaction, and the resulting product is not an ether, but is an alkene along with the alcohol. Okay, we can take also a simple example we can show here. If we have, for example, we'll take a tertiary alkyl halide and its reaction with an alkoxide. Let's take the C2H5OH ONA. Okay, so a negative charge, there will be a positive charge on this, a small negative charge on this, attack of this on the carbon. Okay, but this is not the possible pathway that is followed. Rather, what happens, one of the hydrogens from this carbon, one of the hydrogens from one of the carbons is actually taken by this oxygen, that is taken by this oxygen, this pathway is followed. Okay, and there is a formation of a double bond between this carbon and carbon. As a result, the resulting product is only the alkene, CH3, and we have CH2 here. Okay, in addition to this, here we have the formation of alcohol, C2H5OH. Okay, so this is one of the limitations of Williamson's ether synthesis. Due to this fact, even the symmetrical ethers containing secondary and tertiary alkyl groups cannot be prepared in good yields by the Williamson's synthesis. Similarly, we have another limitation to this method is that we cannot prepare the diaryl ethers. We cannot prepare the diaryl ethers. Why? If there is a reaction between this is sodium phenoxide, its reaction with an aryl halide, and aryl halide is not possible by this particular method. Why? Because the these aryl groups, they do not undergo nucleophilic substitution reactions. Rather, they are capable of showing the electrophilic aromatic substitution reactions, not the nucleophilic ones. Okay, not nucleophilic reactions, rather they are able to show the electrophilic aromatic substitution reactions. As a result, we cannot prepare the diaryl ethers, although we can prepare alkyl aryl ethers by the method, as we have seen an example in the previous slide, but the formation of diaryl ethers is not possible by this particular method. Okay, so this was the Williamson's ether synthesis. In the upcoming videos, we will be discussing other methods of preparation of ether.